Hi, welcome back. Today we're going to be looking at the concept of stress transformations. So we've been looking at this in class, and it is the first step towards calculating what we call principal stresses, which are very important to us when it comes to material failure. So in this case, what we've done, or what the problem asks, it gives a plane stress condition. So by plane stress, we have all of our stresses are in two dimensions only, and shown here. So we have 300 kilopascals tension in the x direction. We have 100 kilopascals tension in the y direction, and we have a shear stress of 200 kilopascals, and that's a positive 200 kilopascals. And by that sense, if we look at the one in the positive x face, it's going up in the positive y direction. So it's positive, positive. So that means it's a positive shear stress of 200 kilopascals. And it says to determine the stresses on a face, rotate it 22.5 degrees clockwise. And by our convention, clockwise is negative. So theta is going to be negative 22.5 degrees. So I've drawn in here the element showing the orientation change, dropping it down 22.5 degrees below the horizontal. I've labeled my new axes x prime and y prime in that or rotation from x and from y respectively. And to be fair, this problem is really just the application of three formulae that we've covered in class. And so I'm just going to get on about solving those, or writing them out, substituting in my values, and then solving them. So we'll start by figuring out what my stress is, my normal stress on x prime. So the formula is sigma x plus sigma y divided by 2, or my average normal stress, and sigma x minus sigma y divided by 2 times cos 2 theta plus my shear stress tau xy times sine 2 theta. So if we plug in our values, we have 300 kPa plus 100 kPa all divided by 2, 300 kPa minus 100 kPa divided by 2 multiplied by cos of 2 times negative 22 and 1/2 degrees plus tau xy, which is 200 kPa multiplied by sine 2 times 22.5. So it's a negative in there, negative 22.5 degrees. And so that is equal to 129 kilopascals. And to go with that, we need to figure out what our normal stress is on the y prime axis. And that's equal to sigma x plus sigma y minus sigma x prime, which makes this one a little bit easier to do. And so we plug in our numbers, we get 300 kPa plus 100 kPa minus 129 kPa, or a value of 271 kilopascals. So the last thing we need to know is what our shear stress is at that orientation, or tau x prime y prime. We have a formula for that, no surprise there. So we have sigma x plus sigma y divided by 2 multiplied by sine 2 theta plus tau xy cos 2 theta. So we go negative, that's 300 kPa plus 100 kPa all divided by 2 multiplied by sine 2 theta negative 45 degrees, a little simpler, plus tau xy, which is 200 kilopascals multiplied by cos negative 45 degrees, and we get a value of 212 kilopascals. So I'm just going to take my reoriented element and I'm going to draw those stresses on it, and we'll see what we get. So I've drawn my element again, and so I'm looking, so it's a positive value. Sigma x prime is 129 kilopascal, so it's still positive, so that means tension. So in the x prime direction, and obviously also in the negative x prime direction, we get 129 kPa. Y prime is positive, 271, so that implies tension. So in the y prime direction and the negative y prime direction, we get 271 kPa. And our tau x prime y prime is also positive. So if I go on the positive x prime face in the positive y prime direction, that would be here. And of course, that gives us the direction for the other four in-plane shear stresses, pointing to opposite corners. And the value there is 212 kPa for each of those four that I've just drawn in. And so there's our reoriented element with their normal and shear stresses shown. So it's a fairly straightforward process, I would say. If there's one spot where people make mistakes in this, is they either don't recognize the sign convention for the angle shift, so theta being plus or minus, and reorienting x prime above or below, or sorry, clockwise or counterclockwise from x, and the same for the y-axis, or they don't recognize the shear stress as either positive or negative, and they get the sign mixed up in substituting in their values. Other than that, this is a fairly straightforward process, and of course, it's leading us up to the next problem that we're going to look at, which is to look at the principal stresses resulting from a plane stress condition, similar to what we've done here. So hopefully I'll leave you a link here to the next video. Hopefully we'll see you there, and we'll look at the plane or the principal stresses from this same element.